Hello dear, welcome back. And you have started watching video on machine learning. And today we are going to discuss uh, one of the most important concept of dimensionality reduction. Yes, you are right. We'll talk about principal component analysis and linear discriminant analysis. Now, if we see that why we need to talk about this, you see, dimensionality is very, very important because everything, whatever we are seeing in the environment, we are capturing mostly using some table, the data, if it is structured data, and if it is unstructured data, just like text, image, or speech. So those are, we are again capturing with the help of representative data. And you see, that creates a problem. And say, what is the problem? You will see, especially if we just take an example of unstructured data. This is an image, okay, say small image of 64 cross 64 size, and there are three channels RGB, so multiplied by 3. So this is equals to, the dimensions will be equal to 1, 2, 2, 8, 8. Although it is not too bad, it is high. What this dimension mean here, you see, this is a matrix 64 by 64. This 64 cross 64 matrix represent the pixel intensity value of all the points of this image. Okay. For a slightly bigger image, you can see that say I have some 1024 cross 24 cross 3 image, then its dimension, ignoring 1024, just we can represent 1000. Okay, so this will be some already 3 million dimension. Okay, and now if I try to train a fully connected neural network, say having having some hidden unit, this is say x1, x2, xn, say we have 2 hidden units, and this is my output. Okay. Okay. So all kind of, So this is already having x vector, feature vector is having 3 million. This is 3 million, and then you see this is say in my hidden layer, say I have 1000 neurons. Okay, so then already you can see the problem here. Just here, the W matrix will be of the dimension of the matrix dimension, and the elements of the matrix will be already 3 billion if you are considering it fully connected layer. So here is a problem, right? It is already very big. So this is also called cause of dimensionality, but how to avoid? Similarly, handwritten digit representation, same thing. Okay, suppose you are trying to just some, this is 20 by 20, this is and with bitmap, so 0 1, that is black and white, so 2 to the power 20 means 400 elements will be there. Okay, and whatever you write, for example, I am writing a handwritten 2. Okay, so these are the pixel values will be 1, others will be 0. So the dimension is really big, 400, 3 billion, all kind of things, simply just to represent and process a little bit of the represented feature. Okay, so that's the problem of dimensional reduction, and it is happening because as on date we have a digital machine and all kind of thing, you see, image, these, that, they are represented by digit, but they are not actually, they are analog. The way we believe that we, our vision process those data is not using this kind of digit, but as long as our computers are there, so we'll have to accept the course of dimensionality, and then we'll have to take corrective actions. What corrective actions could be, we are going to discuss. Okay, that how, you see, one good thing about this dimension, course of dimension, is that out of so many higher dimensions, these are on my area of interest. If I try to recognize this image, or this is my area of interest, and this is out of grid of 400 20 cross 20 grid, out of 400 elements, there are few elements which is touched by my pen, will be of my interest, like that. Okay, so we can judiciously reduce the dimension so that still it is processing can be done smoothly, and not only unstructured data, structured data also, say housing price data. Also, you see, we can have large number of features. Say floor area is one. Okay, floor, housing price depends on number of stories. Say this is feature X2. Total land areas. Okay, surroundings of your house. So that is feature X3. Say. There is another number of bathrooms, number of bedrooms. Okay, so these are all features. Say in this way, I can have some 100 features, which actually will determine the housing price. So this is also problematic, right, in case of structured data. But one beautiful concept which earlier also unstructured data I was trying to focus on here. Out of so many features, you see, the price, there are some main features. Price depends on some main features like floor area. It's common sense, right? Bigger the floor area, bigger will be the price. Number of story, bigger the number of story, bigger will be the price, maybe. Total land areas, okay. So these could be the main features on which the housing price will depend. For example, this is not real. So out of so many 100 features, maybe these three, a number of bathrooms, number of bedrooms, number of drawing rooms, number of balconies, these are all there, but these features are not that important as these features are important. So out of so many features, there will be few features which are of larger interest, and can we figure out those dimensions, okay, features, because we somehow need to reduce the dimension, okay, so that our processing abilities could actually actually process the or find the pattern hidden in the data. And it turns out, yes, the common sense is telling that out of many features, some features will be of interest, and we need to figure out those features. Let us take the example. And exactly this is the reduction of judiciously reduction of dimensions actually can be done by finding some directions, okay, and giving those directions data orientation in those directions more important than other. So that is the main objective of principal component analysis. Say, pictorially I am trying to give you some examples. So these are 2D shapes, right? Okay, as you can see that in this direction more data are there rather compared to this direction. In this direction here also, in this shape also, this is more important because data are oriented, more data are oriented in this direction compared to this. Okay, the same. Okay, so here both the directions are very equally important, like that. Okay, so out of 2 dimension, can we figure out less dimension, 1 dimension, where more data are oriented? Here is a 3D, okay, 3D braid, one slice of braid. Now we can see which is the direction where the data are more oriented. Definitely this is the direction, okay, this is the direction. Then next, what is the direction where most data are oriented? Certainly this is the first choice, this is the second, and then what are the other direction? You see, these directions data are oriented, okay. So this is again the example of a duster. You can see in this direction by virtue of the shape. So this is a pattern, right? In this direction more data are oriented compared to this direction or this direction, okay. So mostly this so that you can visualize, I have given these examples. Mostly the message what you are going to get is, if now I cannot visualize these items but instead I have only data captured, okay, then how to figure out that in which direction data are more important than the other direction, important from the perspective of figuring out the pattern, okay. So here you see, if I try to project, because here it is good but because I can visualize, but when dimensionality are more, you will have only data, you cannot visualize. But through visualization, the same principle we are trying to create, which could be followed there as well. For example, I have an option to project the data. So this is my direction, say E1, or another direction which is perpendicular to E1 is E2, or maybe say I have another direction, this initial dimension, I do not know which direction I should project the data. Now tell me which one is more appropriate. Appropriate means in what sense? I will have to tell you. Say I am projecting the data, say in this direction, then these datas, since the direction and the pattern of the or the shape of the object is similar, the data when I will project, they will be having large distance, this and this, they will be distant apart, okay, and we call in this direction the data will have, when I am projecting all the data. Now the raster is actually data I am projecting, then I can see that, okay, from here to here, the variance, we call it, variance is large if I project in this direction. But say your friend has decided, no, I will project, I have the data, visualization is not there, but here visualization is there. I will project all data in this direction. Okay, so then what you will have, so you will have the less variance of the data. Okay, now which one is preferred? This one definitely is preferred. Why? Larger similarities of the data, or dissimilarities of the data, that means larger variance will be preferred than smaller variance. Why? Because the actual what I am trying to through projection, I am trying to make a representation of the true pattern of something for which data is the representative, right? So if I have this pattern, because I cannot see this duster anymore, I can only see the variance of the pattern if I project here. So that variance is completely different than actual pattern of the data, actual pattern or shape of the object. I think this is clear, right? So in analysis, we will try to find that what is the most appropriate direction along which we will project the data. Okay, so 1, 2, 3, 4, all these directions, appropriate directions should be figured out. Okay, and that is exactly the principal component analysis tries to do. Okay, so here, for example, you can see, if I consider this is my x direction, this is my y direction, yx, this is my z direction. Okay, I, j, k are my unit vectors. So if I just project the, so these are incidentally, now I am introducing some jargon. So they are called the unit vectors or eigenvectors. Eigenvectors is German term that means own or most appropriate or principal or whatever main. Okay, so eigenvector direction, and if I can decide some eigenvector directions and project the data, then larger variance will be in this direction. Then second larger will be in this direction. Third larger will be in this direction, like that. And they are mutually perpendicular directions. Okay, and then I can figure out that what is the most important, and I can choose. If I have now, suppose now instead of 3 dimension, this is huge dimension, 1000 dimension, right? And I do not have processing power to capture the pattern of the 1000 dimensional data. So what I will do, I run PCA, principal component analysis, and try to see that what are the directions where the data are more significant. Significant means in terms of having larger variance. Okay, and I select those directions. So direction 1, more significant, giving some value, say, okay, we will talk about that, what is lambda 1, lambda 2, okay, say. So if I have 1000 cross 1000 matrix, then there will be 1000 eigenvectors we call, and we will just with some eigenvalues, those direction we will find. Okay. Okay. And then why we are doing this? Because now the representation of data with eigenvalue and eigenvector. Means in terms of, say, this is the most significant one captured by biggest value, then lower value. So high to low in descending order. Okay, we can write down the values, and then that's it. This is now I will enter in the design phase. Now with the direction, I know how the data are oriented, in which direction, how much data is oriented, and then I can design an algorithm of how many direction I will choose, and those will be my feature. So now, if it is 64 cross 64 images, okay, out of 64, maybe 8 features, 8 directions will be most appropriate if I run PCA on that, and then I will select only 8, 10, like that, and I will discard all other data which are not so significant and oriented in a direction which are not so significant. So that's the basic objectives. We can reduce the dimension by formulating an appropriate algorithm. So isn't it very simple? I think it is very, very simple, right? Principal component analysis perhaps is the simplest tool, but very elegant and effective tool, easy tool, which can give you an idea of objects feature, okay? That how the objects are represented by eigenvalue and eigenvectors. And then it is my choice, and you can argue, okay, there are many dimensions where you have data, but you have ignored. Yes, I have ignored it because maybe for my requirement, those directions are not that important. And after recognizing with fewer features, similar is the case. For example, face recognition. Your face data will be extremely large if I try to capture every pixel intensity value of your face. Instead, you have nose, you have eyes, and I decide that, okay, those few featured or the directions on which data are oriented across your eyes, across your nose, or across your lip, those only I will capture and I will take for my classifier design. I think that's the idea. Philosophically, that's the idea. Then we will talk more detail about how the algorithm is designed using principal component analysis. Okay. So great. Stay safe and goodbye. Next, we'll start from here and we'll continue for formulating an algorithm based on, again, simple statistics. Till then, stay safe. Bye-bye.